The mechanical gear is the bedrock of modern engineering. Two surfaces, cut with evenly sized teeth, lock together to transfer motion and force. Scale that simple concept up, and you get the industrial capacity to build massive turbines, drive vehicles, and power entire cities. Historians generally agree that this mechanism was invented by Greek engineers living in Alexandria around 300 BCE. But if you look at this diagram detailing the anatomy of a 3-millimeter long hopping insect called coleoptratus, the historical timeline doesn't hold up. Hidden inside the joints of this tiny bug is the first fully functional mechanical interlocking gear system ever found in the natural world. To understand why an insect needs heavy machinery in its legs, look at how it moves. This creature jumps forward at nearly 9 miles per hour by swinging both of its hind legs outward laterally. That lateral swing creates a massive physics problem. If one leg pushes off even a fraction of a millisecond before the other, the asymmetrical force will send the insect spinning wildly off course instead of jumping straight. The obvious biological fix would be to just synchronize the muscles using the brain. But nerve impulses take time to travel. That neurological lag creates a delay that is simply too long to guarantee the microscopic timing required for a straight jump. The insect's biological software is too slow to compute the math. To survive, it relies on a structural hardware solution. Biologists at Cambridge University used high-speed video and scanning electron microscopes to discover how the bug bypasses its nervous system. Look at this technical breakdown. The gear mechanism on each hind leg features 10 to 12 chitin teeth. One leg's physical movement locks its teeth with the other, forcing simultaneous movement within 30 microseconds. Notice the shock-absorbing rounded bases, what engineers call filleted curves. We use that exact same structural design in modern transmissions to distribute extreme stress and prevent gear teeth from snapping off under high pressure. To prove this synchronization was purely mechanical, the researchers designed a rather morbid experiment. They took a deceased Issa specimen and manually cocked its back legs into a jumping position. Then they attached an electrode and electrically stimulated the main jumping muscle in only one of the dead insect's legs. The instant the stimulated leg fired, the mechanical interlock caught hold. It dragged the non-stimulated leg in perfect unison, and the dead bug jumped forward. Interestingly, this gearing is highly fragile, so it's only found in juveniles. When a nymph breaks a tooth, it regrows a new set during its next molt. Adults, who can no longer molt, lose the gears entirely and rely on a sturdier friction-based mechanism instead. But for the juveniles, the electrode experiment leaves no room for doubt. The leg synchronization is a 100% mechanical reaction that requires zero active brain computation to work. We did not invent the mechanical gear. We independently rediscovered a blueprint that was operating in the undergrowth for millions of years before we built our first clock. This table compares the biological gears to human applications. While we forge our machines out of steel and rely on synthetic lubrication, the Issus utilizes flexible chitin layers and naturally renewing fluids to achieve the exact same mechanical output. Studying that biological efficiency actually solves a very modern hurdle in human engineering, the development of micro-robotics. When you shrink a machine down to a microscopic scale, complex electronic sensors start suffering from the exact same lag issues as the insect's brain. To get absolute precision, direct physical mechanics are vastly superior and faster than software. Whether you view it as evolutionary optimization or precise design, the natural world remains humanity's ultimate, undefeated engineering laboratory.